Welcome back, future engineers. In this video, we're going to define truss and discuss the rules for building truss free body diagrams. So let's start by defining a truss. And a truss is no more than slim members joined together at endpoints. And in our class, we are only going to deal with simple trusses, which is just a truss composed of triangles to retain shape. And if this is confusing, I created an animation to sort of help explain this concept. And so in this animation, we have members joined together at their endpoints, slim members, and if we apply a force to the outside, you can see that it sort of loses its shape. There's nothing to stop it from collapsing inward, or collapsing sideways, I should say. But if we take the same system and we put just a member through the middle, making a triangle, you can see how there's a member to push back on that force. And so these horizontal members will act in the X direction, and these vertical ones will act in the Y direction, but this triangle system, or this triangle member in the system, will act in both the X and Y direction. And that's what allows it, or helps it, retain the shape. And so let's go ahead and add that to our definition for a simple truss. It acts in both the X and Y direction. So to demonstrate how to draw the free body diagram for this, let's go ahead and still one of those slim members. And if you notice, I was sure to add the joints at the ends of the member, and I'll call this one joint B, and I'll call this one on the left joint A, because that just makes sense to me, and I'll call the slim member in between them just member. And to draw a free body diagram, we need to take the components of our system and separate them to show how the forces act on each other. And so we'll label each one. We'll call this JA for joint A, and we'll call this member, and we'll call this JB for joint B. And in our class, there are two ways that these components can act on each other. So we'll sketch it again over here to the right. So we can sketch the two different versions of the free body diagram. And if you can't tell, FBD stands for free body diagram. And the two types of ways that these systems can act under are compression and tension. And both of these should be fairly obvious on how to sketch. If we were to put this member under compression, we would have forces pushing inward. And of course, at the joints, we'd have to have equal and opposite forces pushing them outward. And likewise, this member under tension would be pulled apart because it's sort of acting like a rope under tension, which means there'd be an equal and opposite force acting on the joints, pulling them inward towards each other. And because tension and compression are inherently opposite to each other, one has to be positive and one has to be negative. And the general rule of thumb is tension is positive and compression is negative. And if you're thinking to yourself that this system is far too easy, I've got good news for you. It gets even easier. But before we point out how, we need to make some assumptions. And the first assumption is members are frictionless and have no weight. And of course, we know this isn't true, but for our class, to make our math simple enough for us to understand the concepts behind drawing free body diagrams for trusses, we are going to simplify it and say this statement is true. And the second assumption we're going to make is that members can only go under compression and tension. And they are perfectly straight. And again, we know this isn't true. But we need to make these assumptions to understand the simple concepts of drawing free body diagrams for trusses and the math behind it. And the last assumption we'll make is all forces are applied at the joints. So in other words, we don't actually sketch the free body diagrams for members. And so what does this mean? Well, what it means is if I wanted to sketch compression for a truss, I would only draw the joints themselves and the forces acting on them. And so this is what my free body diagram would look like for compression with my joints being pushed outward. We wouldn't draw the members at all. And likewise, for tension, we wouldn't draw the members at all either. We would just draw the two joints being pulled inward by the member. And without the member, this is what joints under tension look like. And let me go ahead and add these back to my system up here so you can compare them. And again, I just want to point out that these two systems, this system and this system, are the same, just this system doesn't have the member in it. And this system and this system are the same, just this system doesn't have the member in it either.
So what's the point I'm trying to make? Well,
if you just look down here, these seem backwards, but if you compare them to the free body diagrams with the members, it makes perfect sense.